Welcome to Cheenta School of Statistics and Data Science. Today we are going to solve problem number 43 of GATE 2022 statistics paper. The problem says that x1, x2, x7 be a random sample from a normal population with mean 0 and variance theta greater than 0. So they define a variable k equal to x1 square plus x2 square divided by sum over of x1 square to x7 square. So we need to check the validity of the following statement, that is the statistic k and summation xi squares are independent. 7fk has an f distribution with degrees of freedom 2 and 7, and expectation of k square is 8 by 63. So let us first check one, that is whether a k and summation xi square are independent or not. So for this we have xi follows IID normal 0 theta for theta greater than 0, and the joint distribution can be written as 1 by square root 2 pi theta whole to the power 7 into exponential of minus half summation I equal to 1 to 7 x square by theta equal to, we can form it as ax curl into beta b theta into exponential of eta theta curl transpose dx, where ax is 1 by 2 pi whole to the power 7 by 2, b theta is 1 by theta to the power 7 by 2, and eta theta is minus 1 by 2 theta, and dx is summation xi square equal to 1 to 7. Now observe that the support of the random variable, that is the distribution, is independent of the parameter, and tx and b theta are non-constant functions with the parameter space being an open interval in R. Non-constant functions and parameter space being an open interval in R, that is theta greater than 0 is an open interval. Hence we can say that the given family normal 0 theta greater than 0 is an exponential family with one parameter, and hence tx is sufficient, where tx is summation xi square. Also note that the natural parameter space is an open set in R. The natural parameter space is 1 by minus 1 by 2 theta, which is an open set in R, and tx b theta non-constant function, which we previously said, that is tx equal to summation x square, is non-constant function. We can get different output by in giving different inputs, and b theta is also same, it is a non-constant function of theta. Hence OPF is also full rank, so we can say that tx is also complete for the family normal theta 0 theta greater than 0. So now we have tx equal to summation xi square equal to 1 to 7 is complete and sufficient for the given family. Now we also have xi by root over theta. This will follow normal 0 1 IID. Hence xi square divided by theta will follow pi square 1 IID. This is because we have, if x1 x2 are independent, then for any function f, fx1 is independent of fx2. Here fx is x square, so we can say this by this theorem. So x square by theta follows chi square 1 IID for I equal to 1 to 7. So we define k equal to x1 square. So the given statistic is defined as k. We can adjust it by x1 square by theta plus x2 square by theta, and denominator is also adjusted by dividing theta. So we get this follows chi square. This is following chi square 2. This is also following chi square 2, and this is also following chi square 5. Hence we get chi square 2 by chi square 2 plus chi square 5. Now we have chi square m by chi square m1 by chi square m1 plus chi square m2. This follows beta m1 by 2 m2 by 2 of first kind. So by this follows beta 1 comma 5 by 2, that is 2 by 2 comma 5 by 2 of first kind. Now observe that summation xi square follows chi square m, since all the variables xi are independent and identical. For m, any m lies between 1 to 7. So now the k has a distribution of beta 1 5 by 2 of first kind, which is independent of theta. Hence k, we can say k is an ancillary statistic here. Now in around 1960, D versus theorem states that if T is boundedly complete and W is an ancillary statistic, then T and W are independent. Now, what is meant by boundedly complete? By complete, we mean there is just a function of some statistic T, which expression if we go to 0 for all theta belongs to parameter space, then this will imply probability of Ft equal to 0 equal to 1. That is, Ft will be identically 0, which is in a set of probability 1 for all theta belongs to the parameter space. Theta. This is mean by complete. Now, by boundedly complete means the f for all bounded functions f. It means if f is an unbounded function, t may not be complete. That is, this condition may not hold. But if f is bounded, t will always be complete. If this condition holds, then we say that t is boundedly complete. So if a statistic is complete, then there exists function f such that expect this condition holds. So if a statistic is complete, then we can say it is boundedly complete also. So we can apply Basho's theorem here. So using Basho's theorem, we get k and summation x square independent, as k is complete sufficient statistic and summation x square is boundedly complete. Summation x square is k is boundedly k is ancillary and summation x square is boundedly complete and sufficient. So now we have to check question number 2. That is whether x1 square k 7k by 2 has a distribution of f with degrees of freedom 2, 5. So for this, which first now we have if two variables are independent, then covariance is 0. But covariance 0 does not necessarily imply that they are independent. But we can say that xi's are independent, it implies covariance is 0. So covariant not 0 will imply xi's are not independent. We will use the fact here only. Okay, so let us find the covariance of x1 square plus x2 square and with x1 square plus x2 square up to x7 square. Now, since xi's are IIT, independent and identical, so for the covariance term, the variance will exist only for the similar variables, and rest will be 0 since covariance of xj equal to 0 for I not equal to j. So we get this will be 2 into variance of x1 square. Now this is x1. Now we have x1 square by theta follows chi square 1. So this variance of x1 square will simply become theta square into variance of chi square 1, where chi square 1 square is a variable following chi square 1 distribution, chi square 1 distribution. So it is coming out to be 4 theta square, which is non-zero. Hence we can say by this fact that covariance is non-zero means they are not independent. Hence x1 square plus x2 square and x1 square plus x2 square up to x7 square are not independent. Now f statistic is defined by two independent chi-square variables, that is chi-square m1 by m1 divided by chi-square m2 by m2, which follows f m1 m2. But where chi-square m1 and chi-square m2 are independent. Okay. Here x1 square plus x2 square and x1 square up to x7 square is not independent, and we get the numerator and denominator not independent, and we cannot say 7k by 2 is following f distribution as the chi-square is not independent. Hence 2 is not correct. Now to check condition 3, what is it said? Let us look at that. Condition 3 said to check whether expectation of x square is 8 by 63 or not. So to check this, we have already proved that k follows a beta 1 comma 5 by 2 distribution of first kind. Hence the expectation would be 1 by 1 plus 5 by 2, as for x following beta mn, it is simply mean beta mn of first kind. Expectation of x is m by m plus n, and variance of x is mn by m plus n whole square into m plus n plus 1. You can simply derive it, try yourself if you not tried previously. So we have expectation of k is 2 by 7, and by using the formula here, variance of k is coming out to be 2 by 7 square into 5 by 9. Now we have expectation of k square equal to variance of k plus expression of k whole square, which is 2 by 7 whole square into 5 by 9 plus 1, which is coming out to be 8 by 63. So we have expectation of k square is actually 8 by 63, hence 3 is true. So we have got 1 is true, 2 is not true, and 3 is true. Hence the option is 1 and 3 is true only. That is option B. Hence option B is correct. So option B is correct. Now the objective of the problem is to check that f distribution only comes from the two independent chi-square variables. Here the two chi-square variables in the denominator and the numerator are not independent. Hence we cannot say that 7k by 2, that is k with some constant adjustment, cannot follow f distribution. This is one thing, and the next thing is to apply Basu's theorem, that is the ancillary and the boundedly complete and sufficient statistics are independent. We used the fact there, so that is another objective. And third one is to check the expectation of variance of a beta distribution of first kind, and then apply it in the area in the problem. So that is all for today. Thank you for watching. I'll see you in the next video. Till then, stay tuned and stay blessed.